Hello, Algebra 2 students. Today we are going to take the next step in our progression of looking at a new function. And today we're going to expand upon the parent function for the exponential graphs and look at all of the different changes that can be made within the equation. So the title of today's lesson is Equations of Exponential Functions. And our objective is to learn to interpret the equations of exponential functions. So please copy the title and the objective. As always, anytime you need more time, hit pause and then press play whenever you're ready to move on. So let's get started. The parent exponential function undergoes many of the same transformations that the other functions we have studied did. Okay, so we are looking at some of the same coefficients and constants and things like that, but as you've seen in the past, we may need to look for them in different places or read them slightly differently than we have in the past. Now, our parent function that we started with last time was simply y equals some base number raised to something to do with an exponent. All right, now what we're going to see is the transformed function is going to look a little bit something like this. Now, I'll explain a little bit more about this double constant thing that you see there, y equals AB. We'll talk about that more here in just a moment. The rest of this should look fairly familiar. In the exponent, which of course is where our variable x resides this time, we have the possibility of a constant in front of x, which can obviously change the value of x and also possibly change the sign of x. X can be moved left and right by way of a change in the h value, and as always, the sign between x and h is negative. And then, of course, we have plus k hanging on to the end of the function, and that will be our vertical shift like it always has been. Okay, so let's take a closer look at these variables here. Okay, h obviously causes your horizontal shift. Okay, and please remember that the minus sign is built into the formula. So if that minus is not there, that means that h must have its own negative to change the sign. K causes a vertical shift, and the sign of K in the formula should be positive. So if the sign has been changed, then K must have done that. Okay, here is the A thing. Okay, I added an extra variable in there. If you look at textbooks and look this stuff up online, you'll see some disagreeing opinions on this. I added the extra variable on there. B is part of the parent function. It is a base raised to an exponent. So what I did is I added an extra coefficient on there that could influence the value of B. And as A comes into the problem, he is going to compress or stretch the graph vertically. So that can kind of pull it upward towards infinity or downward towards negative infinity, or flatten it out as the value of A changes. And the value of C, the effect that he will have is to compress or stretch the graph horizontally. Now, as you're going to learn over the coming days, some of these changes can have the same effect in the graph as some of the other changes. So in some cases, we may change one variable in such a way and then change a different variable in such a way, and the end result may actually end up looking the same. Okay, you'll get a better feel for that over the next few days. Okay, now let's look at some of the exact changes in here. Okay, let's start off with A. Now we already said that changing this coefficient, or as A influences B, okay, that is going to have a direct effect on the variable y. So we're actually going to get some stretch and compression in the graph vertically. Okay, now here are a couple of graphs. Now these guys deal specifically with the parent function. Okay, looking over on the right side, the graph that you're looking on the right side, okay, this is the value when A times B, whatever that product is, when it is greater than 1, we see a graph like that on the right side. And that's what we've seen here, saw last time with the parent function, a graph that comes along the negative x-axis in quadrant 2, turns upward through the y-axis at 0, 1, and then moves up into quadrant 1, turning more vertical. Now, the requirement on the parent function also allowed for the left-hand graph. Okay, x was, or the coefficient b, okay, was allowed to be between 0 and 1. It could not be 0, it could not be 1, but it could have been between 0 and 1. We didn't look at that. Okay, and here's why we didn't. Now that we know a little bit more about the graph, take a look at it. Okay, the one on the left and the one on the right, obviously they are backwards from each other in a left to right aspect. Okay, so when your base is between the values 0 and 1, okay, your graph is going to be reversed. Okay, instead of coming in along the negative side of the x-axis, it comes in along the positive side of the x-axis. Still passes through 0, 1 on the y-axis, but obviously turns upward in quadrant 1 or quadrant 2, depending on where the value of a times b puts this at. Okay, so if a times b is between 0 and 1, we're going to see the guy that's on the left. If it is larger than 1, we're going to see the guy on the right. Now, another thing that could happen is this product of a times b is not limited to being just from 0 to 1 or being greater than 1. That was a requirement of the parent function. But one of the transformations that can be made that would make it not a parent function is a possibility that these values could be negative. So we could have an a times b that is somewhere between 0 and negative 1, like the picture on the lower left. And as you can see, that turned the graph upside down. Okay, because obviously, or apparently what we've done here is changing the product of AB from positive to negative. That has the same effect as reversing the value of y. Okay, so the y values, instead of going upward on the y-axis, made it go downward on the y-axis. And in the lower right-hand corner, again, when a times b is, in this case, smaller than negative 1, okay, so it's going from negative 1 on the x-axis off to negative infinity, okay, then we have the same graph as from above. It's just turned upside down because the y value sign has been changed. Now, looking at this stretch and compression on the x-axis, that deals with the coefficient of x. Okay, so let's look at what happens when the constant c decides it wants to change. Now, in the center, what you're looking at is the parent function. It's supposed to be 1. When c equals 1, then we get this graph. Okay. Now, it is possible that the coefficient of x could be smaller than 1, but bigger than 0, so still positive, but less than 1. And we would see the graph over on the left side. And as you can see, it has been stretched outward from left to right. Okay, so the graph it still passes through 0, 1 on the y-axis, but as you can tell, it's been pulled outwardly on the positive x-axis and the negative x-axis. But over on the right side, if the constant for x gets bigger than 1, then the graph has been kind of smushed inward towards the y-axis. Okay, so those are a couple of changes that we're going to need to know. And of course, these signs can be reversed as well. Okay, so if the sign of x is turned negative, then that is going to change the direction of the x-axis. So if instead of on the left-hand side with c being between 0 and positive 1, what happens if it's between 0 and negative 1? Well, that has swung the x-axis around, so the graph's direction has changed. And if c is negative 1, again, the graph's direction has changed. And if c is smaller than -1, then that is going to smush it in towards the y-axis, but again, the direction has changed. Okay, so just the easiest way of thinking about it is if it is the base that has its sign changed, like we saw on the last slide, that reverses the direction of y. But if it's the constant in front of x that has its sign changed, then that reverses the direction of x. Okay, so let's take a look at a couple of them here. Hopefully we can get through it pretty quick. Let's graph y equals base of 1/2 raised to the x minus 2 plus 3. Now, one of the things that we always kind of want to know when we get started on a new graph, particularly an unknown graph, is it'd be great to have a place to start. Okay, so let's look at kind of a starting point. Now, the only part that's really kind of fixed in the graph of the exponential equation is the intercept with the y-axis. We know exactly where the intercept of the y-axis is supposed to be, and it's supposed to be at 0, 1. However, we have now learned that it can be moved by changing the h and k values. Okay, so let's have a look. In this equation, h has been changed by 2. We see x minus 2. So our little intercept point has been moved 2 units to the right. And also our k value, okay, has been moved as well. And we can see that we have a k value of 3. Now we need to pay close attention. This means a shift, and our shifting point is not from the origin like it has been with our recent graphs. We're going to be shifting from the y-intercept point, which should have been at +1 on the y-axis. So we're going to go 2 units to the right from that intercept and 3 units up from that intercept. And that's going to put our starting point at 2, 4. Okay, so it's real easy to misread this this center point or this intercept point because it's not the way we're used to reading. Okay, but anyway, we're going to generate ourselves an XY chart. We already know that we have a point 2,4 in the graph. Okay, and we can plot that. Okay, now it's kind of important to understand which points we might want to pick to go along with our x values. Okay, which points in the domain should we look at? Now, if we understand the graph and the equation, it should give us a pretty good idea of what kind of points to pick. Okay, so looking at this equation, we can see that our AB, our little base value, has been changed. It is a number smaller than 1. It is positive, but it is smaller than 1. Now that is going to cause the graph to reverse itself, okay, around in an, well, not around the x-axis. It's going to reverse itself in an x aspect, an x point of view, because of that value being smaller than 1. So what we should expect is a graph coming from the right side, mostly horizontal. It's going to hit our point that we have here, and then it's going to turn more vertical to the left. So we should select x values that kind of reflect that. Now it's not a graph hadn't been moved or changed as far as its speed is concerned. So just picking some whole number points here. You might actually want to choose some smaller intervals going to the left because we do know the value is turning upward as it passes through this point. Okay, but picking some values, and I've taken 3 whole steps on either side of the center, okay, or the intercept. I'm sorry, I keep using the wrong term. And we're going to take these points and we're going to plug them into the equation one at a time. Now, this is one of those rare occasions where you're actually going to hear me say the calculator, it can be your friend on this one. Some of y'all have had some big problems with the calculator. And this is no exception. You're going to have problems with the calculator if you cannot ask the calculator the right question. So if you do not know how to type this into your calculator, you absolutely need to ask this question. But we're going to end up with some decimal points, and these are not in a lot of cases, not really easy fractions to work with, not easy fractions to arrive at. So you're going to end up with some decimal points, and your calculator is probably going to be your only source of information unless you're really good with your fractions. Anyway, plugging those 6 values in, we end up with 6 range values to go with them. We can take that information, we can plug it into our graph. Now I ended up with 1 point that is way up off the top of the graph, which is kind of a hazard with the exponential function, and that's why I'd said going to the left from this axis intercept of 2, 4, that was probably a good opportunity to maybe, instead of moving by whole steps to 1 and 0 and -1, maybe some half steps would have been smarter. But after you have your graph or your points, you can complete your graph. And of course, keep in mind, the graph continues in both directions. Do not stop your graph simply because your points stopped. Okay, one more. Graph y equals 2 to raised to the -x plus 1 and then plus 1. Now we're going to go through the same series of questions. We're going to figure out where our starting point is at. Okay. And once again, remember that the exponential function does want to cross the y-axis at 0, 1. Okay, so let's read the changes in the graph. The starting point, it looks like it has been moved on our h value. Our h value is a -1. It should say x minus some number, but it says x plus some number, so that means that number must be negative. So it is a -1, so we're going to move 1 unit to the left, and then from there we are going to move 1 unit up. So from 0, 1, we're going left 1, up 1. That'll put us at 1, 2. Oh, I'm sorry, I just said that incorrectly. Okay, we moved 1 unit to the right, and the reason we moved to the right was because of the -x. That one always catches me. The -x that's in there. Okay, remember, if it's the variable x that has its sign changed, that also causes us to read the value of h differently. So we actually get a double sign change in there, so it is actually a +1. My apologies for confusing you on that. So we've got take our chart. We've got a point to put in our chart, our starting point 1, 2, and there is the plot. Okay. Now we have a negative in front of our x in the exponent. So that's going to reverse the x-axis. So once again, our graph will be coming in horizontally from the right side, turning vertically on the left side of this point. Okay, but no other changes as far as direction is concerned. Our AB, our base value, is 2. That is larger than 1. That is going to cause the graph to be compressed vertically. Okay, so let's see what it does to our graph. Okay, now this time I did select some smaller steps on the left side of the starting point because of that understanding that it is turning more vertical from on the left side of the starting point in this case. Okay, and I don't want to get up off the top of the graph so quickly. Again, I'd rather have some points in the graph rather than off of the graph. Okay, so here we go. Just pick some points. I took whole steps going to the right because that side is going to be mostly horizontal. Took half steps going to the left because that was going to be mostly vertical. And we also have that 2 as our base number. That's going to speed this graph up. It's not going to be in the graph long, so we didn't want to pick too many points that are too far away from the starting point. Plugging these 6 numbers into the equation one at a time, and again, please ask if you do not know how to program your calculator correctly, and we end up with some decimal points. Okay, using those decimal points, we ought to be able to take these order pairs to the graph and plot them, and look how close that came on the left side of the starting point. Even with only taking half steps, we still barely got that third point in the graph. If we had stepped by whole numbers, we would have 2 of these points would have been way off the top of the graph. Anyway, we got our points there, and after you have your points, you can draw your line, and then you're done. This is going to take a little bit of getting used to because you do need to understand the equation a little bit. before you go straight to the graph. Picking the proper domain values is going to be kind of important. Anyway, I appreciate you finding time to get your notes taken care of, and I'll see you in class.